Hello everyone, my name is Ruili Liu from Tsinghua University as well as the University of Electronic Science and Technology of China. This is a joint work from Tsinghua, Alibaba, UTA, and USENIX. I'm going to introduce our paper, DSA-based two-level memory, a tiered memory system that leverages Intel DSA to accelerate page migration. With a growing demand of data-intensive applications, such as graph processing and machine learning, tiered memory hierarchies have emerged as a solution to balance performance and cost. It typically employs a two-level memory with a fast, expensive tier and a slow, cost-effective tier. The fast tier, like DRAM, is directly attached to the CPU, offering low latency and high bandwidth, but is costly and limited in capacity. In contrast, the capacity tier, such as CXL memory or inter-option persistent memory, is CPU-less. It offers large capacity at a lower cost, but with higher latency and lower throughput. To narrow the gap between the two tiers, we need to monitor memory accesses, identify which pages are hot, and eventually migrate hot pages to the faster tier. Our goal is to minimize the utilization of fast tier memory with hot pages. We summarize the three most important insights from tiered memory systems. The first is page migration can interface with application performance. Let's take MEMTIS as an example. Each memory tier runs a dedicated case rate for page migration, with a default CPU utilization threshold of 5%. If we increase this threshold to facilitate page migration, the case rate began to compete with applications for CPU time, which leads to performance degradation. Second, page copy overhead is expensive. We provide the kernel migration process using perf on MEMTIS, and found that 73% of CPU time in migrating pages is spent on copying pages. This includes both 4 kilobyte base pages and 2 megabytes transparent HUD pages, suggesting that HUD pages are commonly found in tiered memory. For PageRank workload, during the migration, there are over 8,000 transparent HUD pages and around 1.2 million 4 kilobyte pages, with HUD pages accounting for 78% of the total memory footprint. This raises a key question. Can we find an efficient CPU-free solution for page migration? A promising way to reduce CPU bottleneck is to offload the overhead to hardware accelerators like Intel DSA. Intel DSA is short for Intel Data Streaming Accelerator, is a high-performance on-chip engine integrated into Intel Sierra Speed's CPUs starting from the 4th generation. It is targeted for offloading cache-coherent memory operations such as data movement, DF checks, CRC checksum, and so on. By offloading these tasks, Intel DSA frees up valuable CPU circles, increasing compute capacity, and scales well to support multiple users. To reveal the potential of DSA in tiered memory systems, we conducted a series of micro-experiments across DRAM NOMAD nodes in kernel space. We tested on a dual-socket server, and the cross-socket peak non-temporary write bandwidth is about 110 gigabytes per second, measured by Intel MEMTIS. Each DSA device was configured with 1 dedicated work queue and 4 process engines. Thus, 1 DSA device maps directly to 1 work queue. To ensure fair comparison with CPU, we used 1 DSA device versus 1 physical CPU core in all tests. And the first observation is straightforward. DSA delivers higher performance than CPU-based copying. However, not all memory copy sizes benefit from DSA. When the transfer size is 32 kilobytes or larger, DSA shows higher performance than CPU. For small transfers, using multiple DSA devices can actually degrade performance. This happens because the submit descriptors are processed in a pipelined fashion, and the initial overheads dominate for small sizes, making CPU copy faster in that range. As the transfer size increases, the submission overhead of DSA can be disregarded, thereby showcasing its performance advantage compared to CPU copying. The third observation is that DSA throughput depends on both the number of work queues and the batch size. First, we fixed the transfer size at 2 megabytes and increased the number of work queues. We observed that latency decreased monotonically and the bandwidth gradually increases until it approached the cross-circuit bandwidth limit. We found that using 4 work queues achieves nearly the max meaning throughput. Similarly, we fixed the transfer size at 4 kilobytes, used only 1 work queue, and varied the batch size. The average copy latency for 4 kilobytes transfers decreased steadily, and the overall bandwidth increased accordingly. We found that a batch size of 8 achieves close to peak through output. Based on these observations, we identified several key challenges that need to be addressed. First, how to directly use DSA in kernel space for page migration. Since naively using DMI APIs and IOMU address translation introduces extra overhead and complexity, we choose to bypass both, enable DSA direct access to physical address in kernel space. Second, how to let both 4 kilobytes and 2 megabytes pages enjoy the benefit of DSA. And third, how to dynamically choose appropriate batch size and number of work queues. To tackle these 2 challenges, we designed a concurrent migration workflow and proposed an adaptable aggregation algorithm. This design takes advantage of both batch processing and multi-work queue parallelism, allowing us to adjust the copy granularity and concurrency level at runtime, thus improving efficiency for different page size. Let's first look at how address translation works with Intel DSA. In user space, DSA supports virtual addresses that are shared with the process running on the CPU. This is so-called shared virtual memory feature. Each process is assigned a 20-byte process address space ID or path ID, which uniquely identifies its address space from the DSA's perspective. When a descriptor enters a process unit, the DSA uses the path ID to look up the corresponding address in the address translation cache. If there is a miss in the address translation cache, the DSA issues an address translation request to the IOMMU, using the path ID to select the correct page table for the target process. The IOMMU then works the appropriate page tables and returns an address translation response, completing the translation. In kernel space, DSA supports the use of physical address. We can easily obtain the physical address from a struct page and use it directly in submit descriptors. One key challenge is that using DSA in kernel space does not trigger any page fault. The page migration process in Linux typically goes through 6 steps. Lock the old page, install a migration PDE, trigger TLB shutdowns, copy data from old to new, install the new PDE, and finally, unlock both pages. However, this mechanism is quite inefficient. Pages are migrated one at a time, in a strictly serialized fashion, leading to high kernel activity time. As a result, we cannot fully take advantage of DSA's performance in this setting. Inspired by Nimble, we reconstruct the migration logic. Instead of migrating pages one by one, we first complete step 1, 2, 3 for all pages, then perform step 4, the data copying, in parallel. And finally, finish the remaining steps for all pages. In effect, what used to be unseparate 4 kilobyte migrations is now merged into a single aggregate migration. This allows us to aggregate the data copying of multiple 4 kilobyte pages. Thus, we can leverage DSA's batch processing capabilities for non-continuous 4 kilobyte pages. To aggregate the data paths for both small and large size pages, we propose an adaptable aggregate algorithm. Before migration, the migrate page list typically contains a mixture of 4 kilobytes and 2 megabytes pages, either to be promoted or demoted in a single migration round. In the first round, the algorithm prioritizes picking out 2 megabyte pages, as they take the longest time to copy. Meanwhile, it scans the list to count the number of 4 kilobyte pages, which is then used to determine an appropriate batch size. Then, the algorithm splits each 2 megabyte pages into smaller slices and distributes them across multiple work queues for parallel copying. For example, assume there are 8 available work queues. Each slice would be 1/8 of 2 megabytes. That is 256 kilobytes. Next, it groups the remaining 4 kilobyte pages into batch lists and submits a batch descriptor to each work queue. The batch size is determined on the number of 4 kilobyte pages and the number of available work queues. In corner cases where the batch size is less than 2, the remaining 4 kilobyte pages are submitted directly to each work queue. Note that the last few lists may not be filled in full. Our algorithm balances the total in-flight data submitted to each work queue, ensuring that the difference size between work queues does not exceed the size of a single 4 kilobyte page. Now, we present our evaluation methodology. Our testbed is a dual-socket server equipped with an async-based CXL expander. And the load latency is about 112 nanoseconds for DRAM and around 300 nanoseconds for CXL memory. We evaluated 5 representative real-world workloads, including graph benchmark, HPC workload, and in-memory data processing. 2 workloads A and B are employed to assess the effectiveness of our adaptable aggregate algorithm. We measure the bandwidth of continuous page migration. The results show that DSA-2LM achieves 15 to 17 times higher performance than CPU-based implementations. With DSA integrated, the overhead proportion of migrated page list in K-migrated case rate dropped from 34% down to 4.2%, compared to original MEMTIS. We successfully applied DSA to other SOTA tiered memory systems using similar approaches, denoted as TPP+, NOMAD+, and Autonoma+ in the figure. And we set the faster tier as 16 and 32 gigabytes. Results show that DSA-enhanced systems outperform their originals in the majority of cases, achieving 12 to 52% better performance in the best cases and 1.2 to 13% performance improvements on average. We use the control group interface to limit the capacity ratio of fast tier and slow tier. When the DRAM to CXL ratio is 1 to 2, DSA-2LM outperforms MEMTIS by 2.5% to 12% in all cases. When increasing the ratio to 1:16, DSA-2LM achieves a 1.8 times speed up in the best case and 28% performance enhancement on average. This significant improvement occurs because the fast tire memory can only accommodate a small subset of hot pages. DSA-based fast page migration enables better adaptation to dynamic access pattern changes. In conclusion, DSA-based two-level memory is the first work to Arlingtonize DSA in tiered memory to the best of our knowledge. We designed an aggregation algorithm for adaptable data paths and leverage batch processing and multiple work queues approaches to facilitate concurrent page migration. Our work is orthogonal and compatible to other tiered memory systems and now is publicly available on GitHub. Thank you very much. I'm happy to take any questions.